Welcome to ScaleUp University. Welcome to the course on designing data intensive applications. This is the lecture number 11 of module 1, and in this lecture we will be discussing describing load. So this lecture is about load. So if we look at the lecture overview, like what we will be discussing in this lecture. So before you ask, can this system scale? You must ask, scale against what load? So this is the core philosophy of this lecture. Like if we just say that can the system scale, that is an incomplete statement. We have to tell scale against what load. So many teams, they talk about scalability vaguely. When a team says our system is scalable, they are often making a meaningless statement, because a statement like our system is scalable, it is incomplete, it is meaningless. The context is missing, because a system handling 1 million static image requests might crash under 1000 complex database writes. So load plays a very important role, because when I talk about the system is scalable against what load, because a system which is handling 1 million static images, because serving static image is not that compute intensive, and that the system which is handling 1 million static images, that system might break, it might crash when the same system is exposed to 1000 complex database writes, because database write is compute intensive as compared to serving the static image. So that's why the load plays a very important role, like what kind of role the system is serving. So load truly defines the scalability. So the lesson we should learn is, you cannot optimize performance in a vacuum. You must identify the bottleneck resources like the CPU, the memory, the input output, and the network bandwidth, because these are like bottlenecks. We cannot have infinite compute power. We cannot have infinite memory like the RAM, IO, network bandwidth. So these resources have bottlenecks. So you must identify bottleneck resources that will be exhausted first under a specific type of pressure. So many teams, they talk about scalability vaguely. That is wrong. So whenever we talk about scalability, we have to define the load, scalability against what load. We have to identify the bottleneck resources as well. Similarly, many teams, they design systems without defining the load. So that's a very big mistake. Without defining the load, they start designing the systems. To make scalability measurable, you must define the load parameters. So you must first define the load parameters, because load parameters makes the scalability measurable. So load parameters are basically the specific metrics that describe what the system is actually doing. Common examples of load metrics or the load parameters, if I talk about, we have request volume. Request volume is a load parameter, like request per second to an API. So request volume is a load parameter. Data volume is a load parameter. The total size of the data set, like scaling from 1 TB to 1 PB, 1 terabyte to 1 petabyte. Concurrency is a load parameter. The number of simultaneously active users or open web sockets. And complexity is the load parameter. The ratio of reads to write. A system that scales for 99% reads looks very different from one scaling for 50% writes, because we know that writes, it is more compute intensive than the read. So a system which is scalable for 99% reads, the same system might crash, it might break for just 50% writes. So read write ratio, the complexity plays a very important role. So now it's very clear that when we are designing the system, first we have to define the load even before starting designing the system. Defining load is very important, because if we define the load using the load parameters, we will make scalability measurable. And the load parameters include the request volume, that is the request per second to an API, the data volume, the concurrency, that is the number of active users or the web sockets, and the complexity, like the read write ratio. And that is why, like, many teams, they consider scalability, they talk about scalability vaguely, they design systems without defining loads, they end up failing under real world conditions. So many teams, they fail under real world conditions. So scalability is the ability to maintain performance by adding resources as the load increases. So what is scalability? Scalability means maintaining the performance by keep on adding resources as the load increases. So load plays a very important role in scalability. If you don't know the load, you don't know which resources to add. For example, if your load is massive spikes in logging attempts, so if the load is the request volume, if the load parameter is the request volume, like the massive spikes in login attempts, in that scenario, storage won't help. If you increase the storage, nothing will happen. Rather, we have to increase the compute or the distributed cache. So if you don't know the load, you don't know which resources to add. So the core idea is scalability is always relative to a specific workload. So whenever we are talking about the scalability, we have to talk about the load, because scalability is always relative to a specific workload. Scalability with respect to a load. And that is what this lecture is about. In this lecture, we will learn to describe load. And if we describe load, if we learn to describe load, we will learn to measure the scalability. So this lecture is where scalability becomes measurable and concrete. So students move from systems should scale to scale with respect to what load exactly. So in this lecture, we will be going through three stages of maturity. So the first stage is the level one, novice. So a fresher or a novice, he will just tell, we need a system that scales. No target, nothing, just a system that scales. So it's a very vague statement. And level two, if I talk about the intermediate, they will make use of the statement like, we need to scale to 10,000 users. So this statement is much better, because here we have highlighted the load. The load is 10,000 users, but still it is vague. We haven't specified what those users will be doing. Those 10,000 users will just be surfing the web pages, or some complex operations will be involved. So that information is missing. So we have the level three, the concrete. So a statement like, we need to maintain a P99 latency less than 200 milliseconds, while the system handles a 10:1 read-write ratio at 5,000 requests per seconds. So now this is the concrete statement, because here we are also talking about the load, and also we are talking exactly what we will be doing. Like the operations will involve 10:1 read-write ratio, and the speed is 5,000 requests per second, and we want a latency of less than 200 milliseconds. So now it's very clear that whenever we are talking about scalability, we have to be very concrete. Scalability should be measurable. And in this lecture, you will learn how to measure the scalability, because load is the key, describing the load. And let us see why systems fail without this. So if you don't measure scalability, then what will happen? You may end up over engineering for wrong problems, because without measuring scalability, we will never get to know the right resources we need. We may over engineer for wrong problems, like unnecessarily we can increase the complexity of the system, or we can under engineer for real ones. We can fail during surge without measuring the scalability. So the very important question we should ask is, scale against what load? So this question, like scale against what load, it will define the success. So now it's very clear that we got an realization of importance of describing the load. Why describing the load is so important when we talk about scalability? Because scalability without defining the load is incomplete, it is meaningless. And this is what this lecture is about, describing the load. So in this lecture, we will talk about what is load, types of load, why defining load precisely matters. We will look at the real world load profiles and load modeling mindset. So all these topics we will cover one by one in this lecture itself. So this is the module 1, trade-offs in data systems architecture, lecture 11, describing load. And we are starting with the first topic of this lecture, that is, what is load? So what exactly is load? So first let us try to understand the definition of the load. So load is the demand placed on a system over time. So load is basically the demand placed on a system over time. So load is not just traffic, rather it is the total demand on your infrastructure's resources. So now it's very clear that when I talk about load, I am talking about the total demand on the infrastructure's resources, like the total demand on CPU, memory, disk, network, and that is the load. So load is basically, load is not just the traffic. Traffic means number of users. Load is not just about the traffic. Rather, it is the total demand on the infrastructure's resources, like how much burden is there on the CPU, the memory, the disk, the network. That is the load. So load represents the volume. Load represents the volume, like how much work does the system must handle. That is the load. For example, 50 million records. Load represents the velocity. How frequently does that work occur? For example, 5,000 requests every second. And load represents complexity. How complex is that work? Because not all tasks are equal. Calculating a user's personalized social feed is exponentially heavier than serving a static about us page. So complexity is very important. So now the idea is very clear that if I talk about load, three things I should consider: the volume, the velocity, and the complexity. How much work the system must handle, that's the volume. How frequently does that work occur, that's the velocity. And how complex is that work, that is the complexity. So load is the total demand. Load is not the just the traffic, it's the total demand on your infrastructure's resources, like the total demand on CPU, memory, disk, and network, and total demand in terms of volume, velocity, and complexity. So that is the load. So now let us look at a very important insight in terms of load. Key insight. So load is a profile, not a point. So load is not a single number. If you tell an engineer the load is 10,000, they can't help you. You have to describe the load profile. So load is not just a number. It's not a point. Rather, it is a profile. So load is something which needs to be described. Load is not just a number like load is 10,000. It is a vague statement. So load is a profile. So you have to describe the load profile. So when I tell that you have to describe the load profile, you have to tell about the traffic intensity. So traffic intensity is like the throughput. Are requests coming in a steady stream, or do they arrive in unpredictable spikes? So this is the key, because see, load is not something which can be constant. It might keep on changing with time, and hence load cannot be a point. It has to be a profile. And we have to describe the load profile. So we have to describe the traffic intensity, whether the traffic is steady with time, or we have unpredictable spikes in the traffic. So that is what the load is, whether it is steady stream or unpredictable spikes. The load profile talks about the data size. As your database grows from 1 GB to 10 TB, operations that were fast can become system killers, because we can imagine that in 1 GB, like when the database size was just 1 GB, the operations which were very fast, when that the size becomes 10 TB, the search and all, it might take a lot of time. The same operations can become system killers. So load includes the weight of the data being managed. So when I talk about load profile, I'm talking about the traffic intensity. I'm talking about the data size. I'm talking about the operation type, like what kind of an operation we are performing, the read operation or the write operation. So the read-write ratio is the most critical distinction. Writes are expensive because they require disk IO and consistency logs. Reads can often be cached. So operation time is very important. Operation type, like what type of operation we are talking about, the read-write ratio. And load profile, it talks about the access patterns. Do users all look at the same hot item, or is the access spread evenly? Like let us suppose there is some sort of a sale is there, or something viral is there, viral tweet. Then definitely there will be a high load on a single data point or a single item. Whereas if the load is spread evenly, so do users all look at the same viral tweet, or is the access spread evenly? A hot key creates a much high load on a single data item or single shard rather than the distributed access. So access patterns also plays a role. So now it's very clear that if I talk about load, load is not a profile. Load is not a point. Load is not just a number, because load is something which can change with time. So load is a profile, and we have to describe the load profile. So to describe the load profile, we have to talk about the traffic intensity, whether the load is a steady stream or they arrive in unpredictable spikes. The load profile talks about the data size. Load profile talks about the operation type, the read-write ratio, and the load profile talks about the access patterns. Now let us look at some examples of load. Now let us look at some examples of load. So the scenario one is the high throughput, wherein we are dealing with 10,000 requests per second. So 10,000 requests per second, this is a network or a CPU load. So 10,000 requests per second I'm getting. So here for high throughput scenario, you need a load balancer and multiple web servers to handle the sheer volume of connections. So if you have a load balancer along with multiple servers, you can handle the high throughput. So 10,000 requests per second, because using the load balancer, you can distribute the request among multiple web servers, and you can do the load balancing. Now the scenario two, like we are discussing the examples of load, the scenario two is the large data volume. So let us suppose you have 1 terabyte of stored data. Now here I am talking about the storage or the index load. So here you need to worry about how long it takes to back up the data or how deep your B trees are getting, because the idea is that when the volume of the data keeps on increasing, especially in a database, just imagine in a database you're dumping data and 1 TB of data got stored, then the searching, the indexing, the storage will be the bottleneck. So here you will be worrying about the backup time and the B tree depth. Now the scenario 3 is the read write ratio. So we are talking about a load wherein the operation, it involves 90% reads and 10% writes. So we are discussing example of load. So we are talking about a operation type 90% read, 10% writes. So this is a caching opportunity, because we know that for reading we can store the information in the cache. So read heavy, so 90% read, 10% write, it means it is read heavy. And since it is read heavy, you can use Redis or CDNs to offload the database. On the other hand, if it would be 90% writes, then there was a need for a write optimized engine like an LSM tree. And the scenario 4 is the traffic spikes. Scenario 4 is the traffic spikes. So we are talking about an example of a load wherein traffic spikes. So burst traffic during peak hours. So this is a provisioning problem. So usually, like in the normal scenario, it is 100 requests per second, but during the peak time, it may get 5000 requests per second. So your load definition must account for the peak and not just averages. This is very important. When we are defining the row load, we should also talk about the peak load. This is very important, because our system should be capable of handling the peak load. Otherwise, the system can break. So the idea is that if we look at this graph, normally the it is 100 requests per second, but during a particular time of the day, or because of some flash sale, the load, it suddenly there was a traffic spike, like 50,000 requests per second we started getting. So we looked at the examples of load, like we can have high throughput load like 10,000 requests per second. We can have large data volume loads like 1 TB of data stored. We can have loads with high read write ratio, and we can have loads with traffic spikes. So these are like examples of load. Types of load. Now we will discuss types of load. So we break the load into measurable dimensions. So we have like different types of load. So the first type of load is the request per second. It is also called as the throughput. Requests per second or throughput. So first let us understand what is it. What is request per second? So the rate of incoming work, that is number of requests handled per unit time. The rate of incoming work, that is the number of requests handled per unit time, that is requests per second. As the name suggests, requests per second, like every second the number of requests, the number of incoming requests handled every second is the request per second. Now request per second is the velocity dimension. It is talking about the speed, like how much requests per second the system can handle. So it's the velocity dimension. It is usually measured as requests per second or queries per second. See, queries per second is usually referred to database hits, because in database The request is called as query. So queries per second is usually in the scenario of database hits, and request per second refers to the hitting the API endpoints. Now let us try to understand the importance of this request per second, the throughput, why it matters. Now see, request per second, it directly impacts the system capacity. If a system can handle more requests per second, it means it has more capacity. So request per second directly impacts the system capacity. It determines the concurrency requirements, and it also drives the scaling decisions. So request per second is a very important type of a load, because request per second will help us to determine the concurrency requirements. Request per second will directly impact the system capacity, and it will drive the scaling decisions. Now let us look at some important nuances with regards to request per second or the throughput. So this is a very important discussion we are making. See, not all requests are equal. Some requests might be very compute intensive. For example, if we consider a read query, so a read query is not equal to a complex aggregation. Complex aggregation is compute intensive as compared to read query. Similarly, a login is not equal to recommendation generation. See, recommendation generation is compute intensive as compared to login. So not every request are equal. And that is why we have to categorize request per second. So request per second alone is not enough. We must categorize request per second. Handling 1000 ping requests is trivial. Handling 1000 generate PDF report can be very massive. So in both the scenarios, the request per second is 1000. And hence now it's very clear to us that whenever we are dealing with request per second, we also have to categorize it. Like the request belongs to which category, whether the request is a compute intensive or a lightweight. For example, 1000 ping request is like very lightweight, but 1000 generate PDF report can be a massive load. So we know that we can categorize the load as request per second. And request per second, when we talk about, it's not just about the number, it is also about the category. We have to categorize the request per second, like we have to categorize the request, what kind of request we are talking about. That is even more important. So not all requests are equal. Similarly, there is a concept of peak load and average load. So see, average load is always misleading. Average load is always misleading, and peak load is more important. Peak load is critical, because the idea is that, let us suppose the peak load is very high, and during the peak load our system may crash if we don't consider it. So peak load is more critical than average load. Average load can be misleading, because average load is just the average of all the different loads at different time intervals. So average load can be misleading and peak load is critical. So if we talk about like why averages can be dangerous, if your average is 100 requests per second, but hit 10,000 requests per second for 5 minutes during a lunch rush, an average optimized system will crash. So systems, they usually fail at peaks, not averages. So when we are dealing with requests per second, if the load is of requests per second, we don't have to just look at the average request per second. Average request per second can be misleading. If we design our system looking at the average request per second, our system might end up crashing, because we have to consider the peak load, the peak request per second. That is even more critical. So that's the idea of request per second or the throughput. Now the next very important type of load is data volume. So when we describe the load in forms of the size of the data volume. So what is data volume? If we try to look at it, so data volume is the total data stored in the system. It is the sheer mass of the information the system manages. So the total data stored in the system, the information which your system manages, that is the data volume, the size of the data. And it is usually measured in gigabytes, terabytes, petabytes. And data volume is the gravity dimension. So we can describe the load as data volume, as the size of the data, and it is the gravity dimension. Now let us try to understand the importance of it. Why data volume matters in system design. So see, as data grows, queries become slower, indexes they become larger, storage cost increases, and backup and recovery becomes hard because as the data keeps on growing, just imagine from gigabytes if we shift to terabytes of data. So as the data grows, the queries become slower because now the search space will increase, or any processing you have to do, it will take time. Queries will become slower, indexing will become larger, storage cost will increase, and backup and recovery will become harder as the data grows. And hence data volume, you have to consider it in system design. Now let us look at an example. So we can describe the load as the size of the data, as a data volume. So an example of it. So on a 10 GB table, an unindexed search takes milliseconds. And on a 10 TB table, that same mistake results in a full table scan that can lock the database and take down the entire site. So the idea is that once the data volume increases, the queries will become slow, the search will become slow, and the system may crash. It may go down. So in such scenarios, when the data volume grows, the scaling often here requires sharding. Sharding means splitting data across servers. So when the data volume grows, we have to split the data across servers. So the key insight, if we look at with regards to data volume, so data volume is like the accumulation trap. And what is this accumulation trap? Let us understand. See, the idea is that traffic can go down, but data always goes up. See, the idea is that traffic is something which keeps on fluctuating. At one point of time, we can have a very high traffic. At another point of time, the traffic might be very low. But if we talk about data, data will always keep on increasing. Data always grows up. And is as it grows, the physics of your system changes. So that is what the accumulation trap is. Unlike traffic, data keeps on accumulating over time. So with time, the data will keep on accumulating. And hence, our system design should take care of the accumulating data. Now we can describe the load as read-write ratio. So read-write ratio is also a type of load. So we can describe the load in terms of read-write ratio. So let us understand what is the meaning of it. What is read-write ratio? So as the name suggests, it is the ratio between the read and the write operation, read operation and the write operation. So ratio of read operation and write operation. So read operation is basically the queries and write operation is basically the updates, the inserts. So read write ratio is the DNA of your workload. Read write ratio, it tells you where to spend your complexity budget. So read write ratio is the strategy dimension. Read write ratio is the strategy dimension. If we talk about some examples of it, so if we talk about logging systems are write heavy. So read write ratio will be very low because more write operations will be there. But banking systems, if we talk about, they will have very high read write ratio, read heavy. around 90% read. So we have different systems optimized for different read-write ratios. So read-write ratio is also a way of describing the load. Low value of read-write ratio means heavy load. Now let us look at the importance of read-write ratio, why it matters. See, if we talk about read, so we can read from cache index. And when we talk about write, write is basically appending the log, batching. So now why it matters is read operation is relatively fast and less compute intensive as compared to write operations. Write operations are more compute intensive, they will need more resources as compared to read operations. Read operations will need very less resources. Read operations are relatively fast as compared to write operations. So that's the idea. So now let us look at some design implications with regards to read write ratio. If we talk about read heavy task, so we can make use of CDN or cache for read heavy task. So the idea is that if users are mostly consuming content like from Twitter news, you can scale by simply making many copies of the data, read replicas, and putting them closer to the user. Like the user, you can use cache, you can use CDN. So the idea is very clear. So the idea is that for read heavy tasks, we just have to make copies of data and put them closer to the user. So that is a strategy for read heavy task. And for write heavy task, like the logs, the LSM path, like if you are recording sensors data, because we know that sensor data is real time data or log, then it will be write heavy. In that scenario, you will be needing systems designed to swallow data quickly without waiting for expensive disk updates. So we will be needing some temporary storage which can, or some temporary data structure which can swallow the incoming real-time data, and then later we can append it or write it on the disk, because disk updates, they're expensive, they take time. So for that, what we can do is for write heavy task, we can make use of something called as message queues. So whatever the data we are getting, we will just keep on pushing it on the message queue, and from there we will be writing it to the disk. So we can make use of message queues, or we can make use of LSM trees. So we have to optimize the write paths, and we have to use the log structured storage. So in write heavy task, we have to make use of a temporary storage which can swallow the data quickly in the real time. Like we can make use of message queues, we can make use of LSM trees. We also have to optimize the write paths so that we can tackle the expensive disk updates, and we have to use log structured storage to make write heavy task more efficient. So these are the design implications. Now we can also describe load using some additional dimensions, and we call those additional dimensions as context dimensions. The context dimensions. So the idea is that to truly understand load, you must also look at these invisible stresses. So now we will discuss some additional dimensions, like some additional types of loads which our system may come across. So we can describe the load using some additional dimensions. We call those additional dimensions as context dimensions. So let us understand those context dimensions. So we have something called as request complexity. So request complexity is also a way of describing the load. So request complexity means how complex the request is, whether the request is simple query or heavy query. See, one heavy request, like calculate my tax returns for the last 10 years. So heavy requests will definitely consume more resources than 10,000 light requests. What is my username? So request complexity is very important. So request complexity, it tells us whether the request is heavy request or light request, because we know that one heavy request can consume more resources than 10,000 light requests. So request complexity is also a very important dimension to describe load. So you can describe the load in terms of request complexity. You can describe load in terms of latency requirements, like whether it's a real time request or a batch request. So a high load system that is allowed to take 10 seconds to respond is much easier to build than a high load system that must respond in 10 milliseconds. So latency requirements. So now the idea is very clear that the system which we are designing can be a real time system, or it can bear a lag. So that is what the latency requirement is. So we can describe the load in terms of latency requirements. So we can have a system wherein we can bear 10 seconds, like it can take 10 seconds to respond, and such systems are easier to build as compared to real time systems wherein the system has to respond in fraction of seconds. So latency requirements is also a way of describing the load. We can describe load in terms of concurrency, that is simultaneous users. Like how many users will be simultaneously accessing our system. So having 1000 users do one thing every minute is different from 1000 users holding open a constant connection, that is WebSockets. So that is what concurrency is. So here what is happening is that uh, in the first scenario we have 1000 users and every user is doing something different. So in our system we have 1000 requests and every request is a different request. In our system, let us suppose we have 1000 requests or 1000 users, they are accessing our system and every user is doing something different, versus 1000 users, they're trying to access the same resource like the WebSocket. So 1000 users, they are holding the same resource, the WebSocket. So these both are different, and hence concurrency plays a very important role, because to handle these both scenarios is totally different. So we can describe the load in terms of concurrency, and in concurrency also we can specify precisely whether the users will be doing different tasks or concurrent users are trying to access the same resource. Now we can also describe the load in terms of fan out. Now let us understand what this fan out is. So see, the idea is that it's very important for us to understand that does one user request triggers one database query, or does it trigger 50 different microservices? So this is the fan out effect. So this is also a way of describing the load, because the idea is that let us suppose we have a user request and we have to look in whether this request is triggering or accessing a database, or is it triggering 50 microservices. So fan out is also a way of describing the load, because here both the requests are very much different. So these are like some of the ways, like some additional dimensions, the context dimensions we can use to describe the load. Why defining load precisely matters. Now we will discuss why defining load precisely matters. Like why should we define the load precisely? So if we define the load precisely, it will prevent wrong architecture decisions. It prevents wrong architecture decisions. See, architecture, if we talk about, it is the art of making trade-offs. Because in systems, we know that we have resource constraints. We have resource constraints, and because of that, trade-offs will always be there. And architecture is the art of making trade-offs. If you don't know the load, you cannot choose what to trade. Because see, the idea is that if we don't define the load precisely, we might either over-engineer or under-engineer the system. If we over-engineer the system, the over-engineering trap. So if your load is only 10 requests per second, let us suppose your load is only 10 requests per second, but you over-engineered and you built a complex microservices mesh with Kafka, Kubernetes, just to handle 10 requests per second. You are just wasting time and money. That is the over engineering trap. Like the load is not that heavy and we are over engineering the system. We are unnecessarily adding resources. We are wasting time and money. So that is a over engineering trap. And similarly, if we don't define the load precisely, we might get stuck in the under engineering trap, wherein let us suppose the load is 50,000 writes per second, but we are just making use of a single relational database to handle the load. And definitely, after a point of time, the database will lock up. It might crash. It might crash in the production. So the important lesson for us, so that's why defining load precisely is very, very important, because the load definition, it acts as the blueprint. Load definition acts as the blueprint that tells you whether to build a bicycle or a rocket ship. So the idea is very clear. Don't end up building the wrong thing. So to avoid that, define the load first. You should first define the load. Defining load precisely is a very important exercise. So even before starting to design the system, first you identify the load and define the load precisely. Then you start designing the system. See, defining load precisely, like if we define the load precisely, it helps identify bottlenecks. See, every system has a weakest link. Any system you design, it might have a weak link. Now, if you define the load precisely, it tells you exactly what the weakest link is so that you can take care of it. So let us understand the bottleneck matrix. So if we talk about high request per second, high RPS, high throughput, the request per second. So if the request per second is high, then your front door and the CPU will catch fire first. So for high request per second, the weakest link will be the front door and the CPU. And when I talk about the front door, I am talking about the network bandwidth. I am talking about the load balancer, because if request per second is high, the load will be on the network bandwidth, the load balancer, and also on the CPU. So the front door and CPU will catch the fire first. Similarly, for large data, for volume, for data volume, for large data, your memory disk will fail. So the weakest link will be your memory disk. So queries that don't fit in RAM will force slow disk reads. And for write heavy request, your transaction logs and disk IO becomes the weakest link. So the transaction logs and the disk input output become the wall, because the database, they can't commit fast enough. And for read heavy task, your database connections may get exhausted. So your database connections will be the weakest link for read heavy task, because when we will be reading, we will be querying the database. And when the load on the database will increase, the database might get exhausted. So in that scenario, you need to offload the pressure to cache, like the Redis, or you have to use some CDNs. So if we define the load precisely, we will be able to identify the weakest link in the system and we can act upon it. So that is what defining load precisely helps identifying the bottlenecks. So if we define the load precisely, it will enable capacity planning. So defining load precisely enables capacity planning. So by knowing the load, by defining the load precisely, you can answer three most important business questions. How many servers to use while designing a system? So for example, let us suppose if one server handles 500 requests per second and our load is 2000 requests per second, we will be needing at least 4 servers plus one more server for redundancy, for fault tolerance. So total we will be needing 5 servers. So we were able to answer this business question because of defining the load precisely. So if we define the load precisely, we will be able to plan the capacity. We will be able to answer questions like how many servers needed to design the system or when the system will break. We can answer questions like when the system will break. If you define the load precisely, you can predict that at the current 10% monthly data growth, your hard drive will be full in exactly 8 months. And when if you get to know when your system will break, you can take actions accordingly. You can take actions proactively. And also if you define the load precisely, you can answer the question like when to scale. So it allows you to set auto scaling thresholds. Like you can spin up a new instance when CPU hits 70%. So defining load precisely, it enables capacity planning. And if you define the load precisely, it enables testing as well. It enables testing. See, the idea is very clear that you cannot load test a system if you haven't defined the load. So in order to load test a system, you have to define the load precisely. Because if you don't define the load test will be meaningless. Like running 1 million simple hello world requests does not prove your system can handle 1000 checkout basket requests. So this is a very important point. Like let us suppose your system is handling 1 million hello world requests. Don't be happy, or like you should be cautious. Like 1 million hello world requests is very different from 1000 checkout basket requests. So 1 million hello world requests does not prove your system can handle 1000 checkout basket requests. So that's why load test is very important. Load testing is required. And for load testing requires realistic simulation. If you want to do the load testing, we have to do the realistic simulation. Like, and for realistic simulation, accurate load definition is very important because accurate load definition will allow you to simulate the scary scenarios like a 10x traffic spike during a Super Bowl ad or sudden influx of 1 petabyte of legacy data migration. So if you accurately define the load, if you define the load precisely, you will be able to do the realistic simulation. Like you will be able to simulate a Black Friday sale or a Super Bowl ad, the spike in ad, like the 10 cross spike. You can simulate it and test your system. You can simulate legacy data migration of 1 petabyte and test your system, load test your system. So load testing requires realistic simulation, and load testing, it also requires validation. It also requires validation. So load testing, it moves the conversation from I think it works. It will move the conversation from I think to we proved it works against the 2026 project load. So load testing is very important because with load testing we can validate our system, and for load testing we have to define the load precisely. So defining load precisely, it enables load testing of systems. So now let us look at a core insight with regards to defining load precisely. See, the idea is scalability without a defined load is meaningless. Whenever we are talking about scalability, we have to talk about load. Whenever we are talking about scalability, we have to talk about load. Scalability without a defined load is meaningless. A system is not scalable in vacuum. It is only scalable relative to a specific type of pressure. If you haven't defined that pressure, you aren't an architecture, you are a gambler. So if we don't define the load precisely, it means we are just gambling in the name of scaling, because there will be no target and it will be a pure guesswork, it will be gambling. But if we define the load properly, if we define the load precisely, like the load is 10K requests per second, the latency should be less than 500 milliseconds, and 99.99% should be the availability time. If this is so, this is the precise definition of the load. So if we define the load precisely, then you will be an architect, you will be a system architect in the true sense, and that's the idea. So that is the importance of defining the load precisely. Scalability without a defined load is meaningless. Real world load profiles. So now we will look at real world load profiles. So see, in system design, treating load as a single static number is a recipe for failure. Like in real world systems, the load is not constant, rather it is fluctuating. So real world systems, they don't experience flat traffic. So in real world systems, flat traffic is a myth. So in real world systems, the traffic is oscillating. So real world systems, they experience oscillations and shocks. Like there will be some peak load, there will be some moments where there will be peak loads, and we call it like the shocks, and the load is fluctuating, and that is what is oscillations. So the real world systems, they experience oscillations and shocks. If your architecture only accounts for the average, like if you just focus on the average load, average traffic, if you just focus on the average, if your architecture accounts only for the average, then it may collapse during the moments that matter most to users. So during the moments of shocks, peak load, the system may collapse. So the idea is very clear that we should not depend on the average traffic, because in system design, average can be a blunder, it can be a disaster. Because if you design a system just keeping in mind the average traffic, then your system will collapse during the peak load, peak traffic, during shocks. So now it's very clear that if we talk about real world load profiles, the load is not like constant or flat. Rather, the system, it experiences shocks and oscillations. So now we will discuss some different patterns, like some different types of real world load profiles. So we have something called as diurnal patterns, that is daily cycles. So what it means, let us understand. See, most systems breathe with the human clock. So most of the systems, they are perfectly in sync, or they are aligned with the human clock. They breathe with the human clock. So when humans are sleeping, the load will be very less. And during the daytime, the load will be at its peak. So that is what the daily cycles means. So if we talk about real world load profiles, we have something called as daily cycles, wherein the systems, they are perfectly aligned with the human. They breathe with the human clock. So we know that morning 3 a.m., when all of us would be sleeping, the load will be very less. But peak afternoon, the load will be touching its peak. So in the late afternoon or evening, the load will touch its peak. So now the architectural response, let us understand that. So how to deal with this? How to deal with daily cycles? So as a system engineer, like in system design, what measures we should take? So the solution for it is the elasticity. So the idea is that we don't have to pay for 100 servers at night, because we know that at night the load will be very less. So that is where elasticity will come into picture. Elasticity is like pay as per you go. So modern cloud environments, they use automatic scaling to match this predictable rhythm, saving cost during off hours. So instead of buying hundreds of servers for 24 cross 7, we will adopt something called as elasticity. So we identify the real world load profiles, and we know that in the night the traffic will be very low, less. So we will use something called as auto scaling. So in auto scaling, what we do, we will start with, like, permanently we might be using only 5 servers, and then during the daytime when the load will increase, we will automatically scale. And during daytime we may use hundreds of servers, and in the night we may use only 5 servers depending on the load. So that is what elasticity is. So we now got a very good understanding that if I talk about real world load profiles, it follows something called as daily cycles, diurnal patterns, wherein the system, it is aligned with the human clock. So the traffic, the load is dependent on the time. And here we use something called as elasticity auto scaling, wherein we scale the servers as and when needed. So if we talk about real world load profiles, we have something called as sudden spikes, burst traffics. So unlike diurnal patterns, these are sharp vertical increases in load that happen in seconds. So sudden spikes, as the name suggests, these are the vertical increase in load, sharp vertical increase in load, which happens in seconds. Like all of a sudden, if something goes viral, then the load on that post will increase abruptly. So the sharp vertical increase is the sudden spike or the burst traffic. So it is the 100x reality. So just imagine a viral post. So we see a sudden spike in the load. So a viral social media post or a breaking news event can send traffic from 1000 to 1 lakh requests per second instantly. Now, what is the challenge in dealing with the sudden spikes? Let us understand that. So systems, they often fail. They often fail to handle the sudden spikes. See, why is it so? Because auto scaling takes time to warm up. So see, the idea is that we already have something called as elasticity into picture. So the idea is that when the load will increase, our resource will also scale accordingly. But now the problem is that with sudden spike, the burst traffic, all of a sudden the load is increased. Like all of a sudden, in fraction of seconds, from 1000 requests per second to 1 lakh requests per second, our system start getting. So all of a sudden 100x the traffic it increased. And auto scaling, it takes time. So that's why the system fails, because it takes time for auto scaling, and our system will not be in a position to handle 100x sudden spike. So that's why system often fails during sudden spikes or burst traffic. Now, what is the way forward? Like, what is the solution for it? How can our system handle sudden spikes? How can our system handle burst traffic? To survive, engineers use caching, load balancing, and asynchronous processing. So we should make use of caching. See, caching definitely it optimizes the read time. Like and the viral post, we can just put it in the cache so that the lag we can overcome it. We can make use of load balancers wherein if we are making use of multiple servers, we can optimize the load. We can distribute the load, and we can use something called as asynchronous processing. So caching, load balancing, and asynchronous processing can observe, it can absorb the blow, the sudden spikes, the burst traffic without crashing the database. So caching, load balancing, asynchronous processing is something which we should consider. Now, if we talk about real world load profiles, we have something called as seasonal variations. So seasonal variations, these are predictable large scale surges tied to the calendar. So these are predictable increase in traffic, and they are tied to the calendar. For example, some festive like Christmas Eve, and I know that like during Christmas Eve in the bakery portals or some e-commerce portal, you might get lots of sale or some Black Friday sale. So that's a seasonal variation. These are predictable increase in load. So we also call it like the Black Friday effect. So e-commerce platforms in India might see a massive multi-day spike during Diwali, while Western retailers prepare for Cyber Monday. Now, how to handle seasonal variations? So see, seasonal variations are predictable. They aren't surprises. We are already aware of it. So proper planning is the key. So teams typically perform load testing months in advance to ensure the system's high availability during this high revenue periods, because we want that, like let us suppose if you are running an e-commerce platform, your goal is to keep the system up during high revenue periods. During the festive season, we want our system to up and run. Our system should be up and running. So what is the way forward? What is the solution? Proper planning. So the idea is that we know when there will be a sudden increase in the traffic. So we have to test our system. We have to do the load testing months in advance so that our system is up and running during high revenue periods. So months in advance, we should do the load testing. It will ensure high availability so that the system will be up and running and it can generate high revenue. If we talk about real world load profiles, we have growth over time. See, what is growth over time? Growth over time means gradual increase in users and gradual increase in data. So we know that with time, as the system, like the e-commerce platform or any web application, if it is becoming popular, so with time, there will be gradual increase in users and gradual increase in data. So that is growth over time. So growth over time means with time, the system will start experiencing more and more load. The traffic will keep on increasing with time. The number of users and the data, it will keep on increasing with time. So that is the growth over time. Now this is the slow burn scalability challenge, because growth over time, it is not a sudden spike, rather it's a slow and gradual process. Slowly this process we see. So it's a slow burn scalability challenge. So it's the compound effect. So now let us understand what the compound effect means. As your user base grows, so does your data volume. So see, the idea is that as the number of users, it will keep on increasing, the data will automatically keep on increasing. So what worked for 1000 users will break for 10 lakh users, because the database queries, it will become slower as the indexes grow. So the idea is very clear that the compound effect, with the increase in the number of users, the data will automatically increase. So that is the compound effect. So uh, the systems to manage the data, like the databases, if it was handling 1000 users, now the same resources cannot handle 10 lakh users. So we will be needing some strategy to deal with growth over time. And that strategy is the structural changes. So to deal with growth over time, as a system design engineer, we should go for a long-term strategy, long-term structural changes like database sharding, or moving from monolithic architecture to microservices. With this, we can handle growth over time. Unpredictable load. Now, if we talk about real world load profiles, we have something called as unpredictable load. For example, some external events, API abuse, bots, DDoS attacks. So these are like examples of unpredictable load. See, all of a sudden, if somebody is trying to abuse the API, hitting the API like some loop, and like from all the like from so many different ways we are trying to just exploit the API. That is the API abuse. Some kind of an automation wherein to we are just sending abrupt traffic to the system, like DDoS attacks. So these scenarios lead to unpredictable load. And this is the chaos dimension of load, the chaos dimension, wherein the system all of a sudden it starts experiencing unpredictable load because of some API abuse, because of some bots, DDoS attacks, some external events. So a DDoS attack isn't user load, but it consumes the same resources. Similarly, bot scrappers can suddenly double your traffic without adding any business value. So see, the idea is that if we talk in terms of economics, we want more and more users, because every user can give us some business. Let us suppose you are running an e-commerce platform. So every user, there is a potential that he might buy something, so he might end up giving you a business. So that load is something which will generate some value, or which has some value, which will add some business value. But here we are talking about unpredictable load. So these are the loads which are an unnecessary burden on the system. These unpredictable load will not add any business value, because just imagine if somebody is doing DDoS attack, or somebody is like scraping the website. So unnecessary load they are increasing on the system, and they are not adding any business value. So now it's very clear that unpredictable load the system might experience, because the system is exposed to the real world, and the real world is very uncertain. So many entities they can attack the system in the real world. So our system might experience unpredictable load. Now the very big question in front of us, how to deal with it, how to deal or how to handle the unpredictable load. So let us discuss the defense. how our system can defend itself from unpredictable load. So system must be designed with rate limiting. So for API, we should have rate limiting in place, and also circuit breakers. Like let us suppose from the same IP address, we are getting like lots of requests, then we should break it. So we should have circuit breakers in place. We should have rate limiting so that APIs cannot be abused. DDoS attacks cannot be performed on the system. So with rate limiting and circuit breakers, our system can reject bad or excessive load. So the system can stay alive for legitimate users. So that's the idea. So we should have a gatekeeper like the rate limiting circuit breaker, which will just reject bad or excessive load so that our system will not collapse because of some unpredictable load, so that our system is available for legitimate users, which will add a business value. So now if we talk about real world load profiles, let us look at a key insight. So the key insight for real world load profiles is design for the worst case. So this is a very, very important insight. So if you are a system design engineer or you are dealing with system design, then you have to design your system for the worst case, identify the worst case, and design the system to handle the worst case. So in the real world, the average load is a myth. The real world load, if we talk about, so in the real world, average load is a myth, and the real world load, if we talk about, it is dynamic in nature. We see oscillations and shocks, like the real world traffic is fluctuating. There is burst spikes, and we also have unpredictable load. So systems must handle not just the average load, but the worst case scenarios. So design systems for the worst case. So you must define your load based on peak performance and worst case scenarios to ensure true resilience. So if you define your system, or like when you're designing your system, you should define the load based on the peak performance and the worst case scenarios. And if you do that, your system will be resilient. Load modeling mindset. Now we will discuss load modeling mindset. So let us try to understand how good engineers they approach system design and performance. Let us try to understand how good engineers they approach system design and performance. So see, good engineers they define the load explicitly. So before even starting to do the system design, the first thing the good engineers they do is they define the load explicitly. So define the load explicitly. That's the key. So a good engineer treats load as a contract between the business and the infrastructure. So load should be treated as a contract between business and infrastructure. So we should always go for realistic assumptions. So load is a contract between business and infrastructure. So the business goals is like the growth. Business wants increase in load. It wants more and more users, more and more features. So business goals are growth features. So that should be in sync with the infrastructure. As more and more user increases, as the user base increases, the number of features increases, the infrastructure should also scale accordingly. So load acts like a contract between the business and the infrastructure. And also we should always go for realistic assumptions. Instead of saying we want to handle everyone. So we want to handle everyone is not a realistic assumption. It's a vague and unhelpful assumption. So instead of saying that, the good engineers, they say we are designed for 5,000 concurrent checkout sessions. So good engineers, they explicitly precisely define the load. Like the system is designed to handle 5,000 concurrent checkout sessions. So here we have specific and actionable goal. And good engineers, when they define the load explicitly, they also consider the constraint filter. So this is very important, the constraint filter. So here constraint filter means defining the limit. So by defining the limit, the good engineers, they can say no to features that would violate the system's physical limit. So the idea is very clear that, okay, the good engineers, they define the limits, they define the boundaries for sustainability so that they can say no to features that violate these boundaries, these limits, or they can demand more budget to increase those limits. So now it's very clear that good engineers, they define load explicitly. Also, the good engineers, they think in terms of distributions, not averages. So average or the mean latency or average or the mean load is almost always a lie. So now when we talk about load, average can be very dangerous, and average is like always a lie, because average, it hides extreme cases. For example, if 99 users have a 100 millisecond response time and one user has a 30-second response time, in this scenario the average looks okay, but in reality the system is broken for that one user for whom the response time was 30 seconds. So the reality is disastrous. So now it's very clear that whenever we are talking about the load, we are talking about the latency, never trust on the average. Average is almost always lie, because here the average will give us some good numbers, but in reality there was a user for whom the response time was 30 seconds, for whom the system got broke. So we should always consider the P99 mindset. So good engineers look at percentiles. They ask, what is the experience for the unluckiest 1% of our users? So P99 means, what is the P99 mindset? The P99 mindset means looking into the experiences of the 1% users for whom the system got broke. So that is the P99 mindset. We are not at all bothered about the 99% users who got perfect response. Rather, we are bothered about 1% users for whom the system did not responded properly, or the system took lots of time to respond, or some wrong response. So what is the experience for the unluckiest 1% user is the P99 mindset. So that is what think in distributions and not averages. So whenever we are designing system, we should think in distributions. We should always think about 1% unluckiest users. And there we will be able to identify the bottlenecks of the system. We will be able to identify why the system did not responded properly, so that we can take actions. So why it is matters, why it is important, like think in distribution and not averages, the importance of it. So in a microservices environment, one slow request in the tail of a distribution can cause a backup that eventually throttles the entire system. So let us suppose we have a microservices architecture wherein there we can see some series of events and like A, B, C, D. Let us suppose the response of B is taking lot of time. Because of that, the entire system will suffer. Because of one slowdown, one slow request can throttle the entire system. And this is what is the cascading failure. So that's why it's very important to have the P99 mindset. Like, look for extreme cases, look for the scenarios where the system was not working properly. We should try to find the reason for the slow request so that we can take actions accordingly. So good engineers, they ask some important questions like, what is the peak request per second? So good engineers, they are always focused on building the pipes for the flood and not the stream. Like they are focused on building the pipe for the peak hours. So if we get to know the peak RPS, then we can customize our system to handle that peak RPS, request per second. Good engineers, they ask questions like, what is the worst case scenario? So good engineers, they simulate the perfect storm, because once the worst case scenario is clear, they do the load testing on it. Like, database is re-indexed, it's Black Friday, primary cache down. So these are worst case scenarios. Like, the worst case scenario is doing re-indexing of a database. It's a worst case scenario. Abrupt traffic or sudden spike during Black Friday sales. It's a worst case scenario. Primary cache, it went down. It's a worst case scenario. So good engineers, they identify the worst case scenarios and they ensure how to handle it. And they will also look at, does the system failed gracefully, showing a busy page, or does it experience a cascading failure where everything dies? So the good engineers, they ask for worst case scenarios, they look into the worst case scenarios, and they also try to figure out how the system responded to the worst case scenarios. Did the system failed gracefully by showing a business busy page, or showing some abrupt, like some genuine message, or the system just abruptly failed, keeping the user clueless? So the good engineers, they ask questions like, what is data growth rate? What is data growth rate? So good engineers, they look at the storage velocity. Like, if we add 500 GB a month, our current 5 terabyte drive dies in 10 months. A good engineer starts the migration plan in month 5. So a good engineer asks, what is the data growth rate? So once the good engineer knows about the data growth rate, he will get to know that, okay, the current storage capacity is 5 terabyte, and every month we are getting a storage, like a load of 500 GB. So every month 500 GB of data is getting added to the system. So he will do the calculation and he will realize that in 10 months the hard disk will be full. So in the month 5, he starts migrating. He starts upscaling, adding more storage, and doing the migration. And the good engineer, he asks question like, what happens during spikes? So good engineers, they focus on elasticity and panic. So does the system panic and crash because it can't spin up new servers fast enough? They might implement queuing or back pressure to tell the influx of users to wait in line rather than letting them break the door down. So the good engineers, they understand, they analyze the spikes, how the system behaves during the spikes, and if they see that the system crashes because it takes time to scale resources, to auto scale resources, it takes time. And if the system is not able to handle the spike, if the system is crashing, then the good engineers, what they do, they implement something called as queuing, wait in line, or back pressure. So the idea is that when there is a sudden spike, instead of flooding all the requests to the system, we maintain a queue, and one by one, we send the request to the system. In this way, the system will not die, the system will not crash. So, by answering these four questions, the engineer turns scalability from a buzzword into a predictable resource plan. So, finally, we completed this lecture. In this lecture, we saw load defines system demand. We saw that load includes request per second, data size, read write ratio. Load must be defined precisely. Real world load is dynamic and unpredictable, and scalability is always relative to load. Scalability is not just about numbers, how many users, rather, it is about the load. What is the load? And when I talk about what is the load, I am talking about what is the request per second, what is the data size, what is the read write ratio. So, the core insight which you can take from this lecture is you don't design systems for users, you design systems for workloads. So I hope you got a very good understanding of the concepts that we covered in this lecture. So do subscribe to our YouTube channel ScaleUp University for more such interesting lectures and courses. Thanks for watching. Thanks for your time.